Okay, so let's look at problem 7. So this was one of the 2-pointers. So problem 7 and 8 were more difficult than the other problems. But this one in particular we pretty much did in class. The only difference between this and the one in class is the pulley and the cable and the force of gravity. But other than that, it looks exactly the same. So just to refresh your memory, we have two masses, M1 and M2. We have the forward direction shown here. Between the two masses is a cable, and the cable has some compliance. We're modeling it as a spring there. We say the pulley is massless and frictionless, and what that implies, and you know, some people ask that, is that the tension is the same in the cable. So whenever force is on M1 is going to be equal and opposite to the force on M2, which is the same thing we had if there's just a spring between them. So the cable adds nothing substantive to the problem other than the change in direction. M1 also has a damping force acting on it. So going over to our solution, we see two free body diagrams, right? So here's M2 here with two forces acting on the spring pulling up, the mass of, or the weight of gravity, the weight of the mass, or the force due to gravity, pulling down. Over on M1, we see the input force pulling to the right, which is in the positive direction. And as we kind of do our little thought experiment, displacing the mass to the right means the spring will resist motion. So we note the spring force pulling to the left. We note the damping force pulling to the left. And again, making sure Fk is consistent on the two masses. So if it's pulling, it means the spring's in tension, and if the spring's in tension, it means over on mass 2 that force has to pull up. So applying Newton's law to these two masses is summation of forces equals mass times acceleration. Now at this point, even though I showed velocity on the drawings and I explicitly called out velocity, I realized at a later date that what we really need is x's here. We will redo this problem in state space form and show how to do it without the x's, but for now most people saw that, yep, we need to have x's here. So the acceleration is x double dot, so the first equation is m1 x1 double dot is equal to the input force minus the spring force minus the damping force. The second mass has just the spring force and gravity. So a little aside here for people who are not familiar with free body diagrams. The point of the free body diagram is to find just what forces are acting on the mass. Once you have those correctly, go from them. I had some people talking to me about M2, wondering how the damping force F sub B affects M2. It doesn't. See, it doesn't show up on the free body diagram, therefore you don't put it in. Okay, there's an implication B will show up in the characteristic equation, but that's what the math will tell you when you do the modeling. Okay, so the only thing left to do here is to make sure we define the springs correctly. So F sub k is equal to k x1 minus x2. Again, think of that positive, that virtual displacement, that imaginary displacement of x1 in the positive direction. And if x2 is 0, then the signs all work out. If x2 moves up, it's going to actually, without x1 moving, it's actually going to push the spring, compress the spring, and push m1, which would be a negative force, and that's why there's a negative sign on x2. The damping force is just times the b times the velocity, the derivative of x1. Now as we move forward here, I think it's really important to realize that when you have multiple variables, x1, x2, multiple masses, m1, m2, to be just meticulous about subscripts and be careful. Give yourself some room. Write in bigger letters if that's what it requires. But be mindful of that. So what I'm doing here on the left hand side, I'm looking at the x1 double dot equation. On the right hand side, I'm looking at the x2 double dot equation. And I just do a little algebra, right? Group the derivatives of x1 on the left side, everything else is on the right side. Over here I'm grouping the derivatives of x2 on the left side and everything else on the right side. And so what we have are two differential equations, both second order, but coupled. Here's a kx2 term in my x1 equation. Here's a kx1 term in my x2 equation. We have an input force F, and we have this mg here. And strictly speaking, mg is an input, all right, because it's not one of the other variables. But as we talked about in class, that for linear systems, we will assume it away by assuming the static displacement of the spring counteracts that. Okay, so and that's what I'm saying here. At this point, I'm going to get rid of mg by stipulating that x1 and x2 are referenced to some points such that when the difference is 0, that's the static displacement of the spring. There's a more formal mathematical way of describing that, of redefining our variables. At this point in time, let's not do that. Let's just say, hey, I'm going to assume the static displacement. And all I'll ask you to do is be aware, be mindful of the fact that you're making that assumption, because there will be times, probably not in this class, but there will be times when that assumption's not available to do, and that's if the spring stiffness is nonlinear and is defined by, relative to its zero of that nonlinear function is the free length of the spring. Then you're going to have to work on that a little differently. Okay, so if I want to get a differential equation in just x1 in my inputs, I got to eliminate x2 out of this equation here, right? Well, I'll solve this equation for x2 using their d operator. So we go from m2d squared plus k times x2 equals these guys, and at this point this paragraph kicks in. I'm saying, you know what, mg is going to be gone, and so x2 is equal to this function of x1. So that's nice, neat, compact. Substitute that back into our differential equation in x1. So here's the d operator acting on x1 from our original equation. There's the f, and remember it was kx2, but now it's k times this quantity. It's now a case of getting rid of the denominator. We don't like that. It doesn't help us turning it back into a differential equation. So we multiply through the equation like that. So this polynomial will be multiplied by this d squared. This f will be multiplied by this polynomial. And then I'll just have k squared x1. And that's what we see here. Two polynomials multiplied together times x1. This polynomial times f. There's the k squared. Group the terms. You'll find a k squared that comes out of this multiplication. That will be canceled by the k squared on the right hand side, and we have this fourth order differential equation. The coefficient is m1 m2 on the fourth derivative, m2b on the third derivative, m1k plus m2k on the second derivative, kb on the first derivative. Notice there's no linear term, there's no non-derivative term. x1 doesn't show up here. That's an interesting point about some systems that we will focus on later, but I just want to point that out. If there's no non-derivative terms of the output variable, that makes it a different kind of system. And then this polynomial times f turns out into a derivative form. And I noticed here, see, I make mistakes too. I sometimes drop things. So notice here, this derivative, this polynomial is m2d squared plus k. I dropped the d squared to go from this point to this point, which means this needs to be a second derivative term. I will correct that, and what's posted will be the right answer, but showing up in this video is a mistake, right? So that's the answer to let's see which part of the problem was. Write the differential equation that describes the velocity of m1 as a function of the force F. Okay, so interestingly enough, we could do that. I did it in terms of the displacement x1, but if we go back to the solution, we'll see, since I don't have any non-derivative terms, I can do this in terms of velocity. In other words, this is velocity. That's the first derivative of velocity. That's the second derivative of velocity. And that's the third derivative of velocity. So this is a fourth order differential equation, but we can recast that as a third order one. And what we'll find as we go forward, this is clearly a third order system. It should be able to be represented in a third order differential equation, which it can. Excuse me. So kind of summarizing here the first part, you can recast this in terms of V1, and this is a second derivative of force. Okay. Now if we want to get it in terms of the velocity of the second displacement or velocity, x2 or v2, we just do the same process but the other way around. We'll solve the first equation for x1, And so we get x1 is equal to f plus kx2 divided by this polynomial m1d squared plus bd plus k. Substitute in that to the right, the x2 equation. So here's the derivatives of x2. This is what now x1 equals. And you end up with a very similar thing. Notice the polynomials, the two polynomials we're multiplying together are the same ones we multiplied earlier, which means we'll get the same polynomial out. We have the same k squared term times x2 showing up here. That cancels out like it did before. And we have the same polynomial in D that multiplies x2 that we had previously multiplying times x1. Our input's a little different. Instead of the second derivative of the force, we just have k, and that's the difference equation that comes out here. And again, like the previous one, there's no non-derivative terms of x2, which means we can recast this in terms of v2 if we wanted to. I asked you to write the two characteristic equations, and the fact is they're identical, and that's not an accident, right? And I mentioned this in class. I'm going to just keep harping on this. Regardless of what we choose as the output variable, regardless of what we're interested in looking at, the characteristic equation, which reflects the fundamentals of the dynamics of the system, is always the same. Okay, so that's, I just want you to really keep that in mind. And this is actually, if you're it's important to get the right answer. Well, one way to make sure you get the right answer on this is to do this. Look, recast the problem for two different output variables and make sure you get the same characteristic equation. It's a great internal consistency check. I asked, I think that was an extra credit, right? So write the characteristic equations, extra credit. What values would you need to know at time t equals 0 of the problem? So what are the initial conditions? And it's a fourth order differential equation. So you would need to know for initial conditions. Now, thinking in terms of the fact that this could be recast as velocity, you'd only really need 3. So you need this. This would be the third derivative of displacement, or the second derivative of velocity. For the electrical engineers, you may not have heard of this. That's kind of an odd term, but we actually have a word for it. It's called the jerk, as opposed to, there's displacement, velocity, acceleration. That next derivative is the jerk. And it comes in, it's important to see in CAM design, but that's about the only place you ever see it. If you recast this in terms of velocity, then you would only need 3 differential equations, the 3 initial conditions: velocity, acceleration, and jerk. Which tells me that if you were to actually solve this problem with numbers, this initial condition would be meaningless, right? It wouldn't come into play. Okay, so that's the solution to problem 7, again, very similar to what we went through in class. The notes are there, and I hope it makes sense.